Core banking views, building foundational analytics and summaries. We will learn how to create core banking views using Python and pandas. This problem is important because banks need to aggregate data for regulatory reporting, customer insights, and risk management. By working through business-driven examples, you will learn how to assemble transaction, customer, and account data into meaningful analytics. We will build a simple but powerful foundation for real-world banking data analysis. You will gain skill at using Python to create data aggregations, summaries, and tables essential for everyday banking operations. Running the cell now. Before we start, let us ensure we have all the Python libraries we need for banking analytics. We import pandas, the most common library for tabular data and analytics. We import NumPy, used for fast, scalable numeric calculations. We import warnings to manage any Python warnings about data manipulation. We set Python to ignore warnings for a clearer experience. We set the random seed to 42 to ensure reproducibility across runs. Running the cell now. Now we are ready to start building our synthetic banking datasets. Try changing the seed to see how it affects random output. Understanding core bank data, transactions, customers, accounts. Transactions are records of customer payments or deposits and contain dates, types, and channels. Customers have attributes like region and segment, and are linked to their accounts. Accounts track balances and account types like savings or check, with unique identifiers. Beginners often miss that real banking data is always relational, all tables are linked by IDs. Data quality is critical, duplicated, missing, or mismatched IDs cause broken joins and bad analytics. Running the cell now. Let us synthesize a banking transactions dataset with 1,000 rows to mimic real operational data. We set the number of transactions to 1,000. We set the number of unique customers to 200. We begin constructing a data frame using Python dictionaries. We create a unique identifier for every transaction. We randomly assign customer IDs to these transactions for realistic linking. We generate realistic transaction amounts using a normal distribution. We randomly assign debit or credit transaction types. We randomly distribute the transactions across all common banking channels. We generate hourly transaction dates starting from January 1, 2024. We close the data frame definition. We print the total dimensions of the data to verify size. We display the first 3 transactions for a quick preview of the data. Running the cell now. This output shows a data frame of 1,000 transaction records linked to 200 customers via the customer_ID. Notice each transaction has key attributes including amount, type, debit or credit, channel, and a timestamp, reflecting the rich, relational nature of the data. This setup highlights how banking data ties multiple tables through IDs, reinforcing the importance of maintaining these links for accurate analysis. Try changing channel choices to see how channels affect transaction distributions. What would happen if you increase n_customers to 500? Now let us set up a basic customers table. This will help us analyze transactions by customer attributes. We generate a list of 200 customer identifiers. We construct a data frame to store customer details. We set every row to have its customer ID. We assign the first 150 customers as retail and the last 50 as business. We divide the customers equally between metro and regional regions. We close the data frame definition. We print out the table dimensions for verification. We preview the first 3 customer records to check segmentation and region fields. Running the cell now. This output shows the customer's data frame with 200 rows and 3 columns, representing unique customer IDs, segments, and regions. Notice how segments are split into 150 retail and 50 business customers, and regions evenly divided between metro and regional. This structure highlights the relational nature of banking data, where customer attributes must be cleanly defined for proper linking to accounts and transactions. Try switching the split between metro and regional customers. What types of questions could you answer with more customer attributes? Banking views rely on knowing account associations. Let us synthesize a minimal accounts table for our examples. We create a new data frame representing all accounts in the bank. We generate account IDs that are unique and easy to identify. We map each account to its customer using the customer IDs. We assign account types randomly so we can practice type-based grouping. We generate open dates spaced at regular intervals for realistic account creation timing. We end the accounts data frame. We print the accounts table shape to verify that every customer has exactly one account. We show the first 3 accounts. Look for different types and opening dates. Running the cell now. This output shows the accounts table with 200 rows and 4 columns, confirming the dataset size and structure. Notice each account has a unique account underscore ID and is linked to a customer underscore ID, illustrating the relational nature of banking data. This setup is key for connecting accounts to customers in later analyses, ensuring accurate joins and insights on account types and timelines. What would change in business analytics if a customer had multiple accounts of each type? Suggest additional fields useful for product managers. Let us start with a simple example: count how transactions are distributed across banking channels. We print the number of transactions conducted in each channel. This quickly shows channel popularity. Running the cell now. This output shows the distribution of transaction channels, highlighting that ATM is the most frequent channel, followed closely by POS, branch, and online. Notice the counts are fairly balanced, indicating customers use multiple channels for transactions. This reinforces the lesson that understanding channel usage patterns is key in analyzing core bank data and ensuring accurate joins across related tables. Next, try to plot channel usage with Matplotlib or Seaborn. Why do banks care about channel distribution? Now we want to find the average transaction amount by type, either credit or debit. We use Group B to compute the mean transaction amount by transaction type. This summarizes the typical payment versus deposit. Running the cell now. This output shows the average transaction amount grouped by transaction type, with credits averaging about 150.54 and debits slightly higher at 152.88. Notice how grouping by this transaction underscore type column reveals spending versus incoming funds trends, highlighting the importance of categorical segmentation in banking data. This illustrates how relational transaction records can be aggregated to uncover key financial behaviors. Explore further, what happens if you count transaction underscore type occurrences as well as means? Could outliers impact the mean? A core skill is visualizing distributions. Let us plot transaction amounts to spot patterns or issues. We plot a histogram of the transaction amounts for quick visual distribution insight. Running the cell now. The histogram shows the distribution of transaction amounts, highlighting the range and frequency of values across all transactions. Notice how the shape reveals whether most transactions are small, large, or spread out, which helps in understanding customer behavior and detecting anomalies. This visual confirms the amount column's data quality and supports linking transaction details to customer and account insights in relational analysis. Try adjusting the number of bins or the color to make this histogram clearer. Can you spot anything unusual? Intermediate. Let us aggregate daily total flows to understand volume over time, just like a bank would. We group transactions by the date, ignoring time, and sum the total value for each day. We print the first few daily totals to spot trends and check for errors. Running the cell now. This output shows the total transaction amounts aggregated by each day, highlighting how transaction values vary day to day. Notice the dates as the index and the summed amounts, which helps reveal overall daily activity trends. This step is key in understanding how to summarize transactional data by time, an essential skill when working with relational banking datasets. For practice, can you also calculate average daily flow and plot trends for 2 weeks? How might holidays impact total flow? Let us slice our banking data by both channel and transaction type. This is a common business reporting task. We use pandas crosstab to create a table of counts by channel and transaction type. We print the resulting summary to view how activity splits across business axes. Running the cell now. This crosstab shows the count of credit and debit transactions broken down by each channel, such as ATM or online. Notice that some channels, like ATM and POS, have more credits than debits, while others, like branch and online, have a more balanced count. This output highlights how transaction counts vary by channel and transaction type, reinforcing the lesson that analyzing linked attributes across tables is key to understanding customer behavior in banking data. Try creating a crosstab showing channels versus customer segment. How does segment affect channel use? Let us join our transactions and customers to analyze channel activity by customer segment, essential for product teams. We join the transactions table to the customers table using the customer_ID key. We use Group B to count transactions for each combination of segment and channel. We print out the crosstab of customer segment, showing how channels are used by different customer groups. Running the cell now. This output shows the count of transactions by channel for each customer segment after merging transactions with customer data on customer_ID. Notice how the retail segment has consistently higher transaction counts across all channels compared to business, highlighting segment-specific behavior patterns. This demonstrates the importance of proper joins in relational data to combine customer attributes with transaction details for meaningful aggregation. For further practice, can you group by region too? Why does every banking view require relational joins first? Regional performance is crucial in banking. Let us analyze the average transaction amount by region. We group the merged dataset by region and compute the mean transaction amount. We print the mean amounts to see differences between metro and regional customer spending or deposits. Running the cell now. This output shows the average transaction amount grouped by customer region, highlighting that metro and regional areas have very similar mean transaction values around 151 to 152. This confirms the code's intent to summarize transaction behavior by linking customer region data with transaction amounts, emphasizing the importance of correctly joined tables for meaningful regional comparisons. Try filtering for only debit transactions. How could you explain this result to a product manager or analyst? Let us build a reporting view banks use daily, total flow by region and transaction type. We create a pivot table to sum the amount in each region by transaction type. We print the result, which banks can use for daily inflow and outflow tracking. Running the cell now. This pivot table summarizes the total transaction amounts by region and type, showing sums for both credits and debits. Notice each region has similar magnitudes for both transaction types, reflecting balanced inflows and outflows. This output highlights how linked tables enable grouping and aggregation by meaningful categories, reinforcing the relational nature of bank data. Can you extend this idea to show flow by both segment and region? Where would a branch manager focus next? Advanced, let us calculate account penetration by region, a key metric for regional banking heads. We join account and customer data to connect accounts with region. We group the merged data by region and count how many accounts each contains. Running the cell now. This output shows the count of accounts per region by merging the accounts and customers tables on the customer ID, demonstrating the relational link between these tables. Notice that both metro and regional areas have exactly 100 accounts each, highlighting balanced data distribution and confirming that the join on customer ID worked correctly without data loss. This is key for ensuring accurate, region-level banking insights in real-world datasets. For practice, how could you measure growth in accounts if you had latest open dates? Why do many-to-one joins matter? Let us identify our most active banking customers by transaction count, as a relationship manager would. We count transactions for each customer, identifying activity levels. We sort customers by activity and take the top 10 most active ones. We print the transaction counts for the top 10 customers so managers can focus on them. Running the cell now. This output shows the top 10 customers with the highest number of transaction records, highlighting that some customers have 10 or more activities logged. Notice how the counts reveal customer engagement levels, which is crucial for understanding transaction frequency per customer. This reinforces the lesson that linking transactions to customer IDs enables us to analyze activity patterns and detect key customers in relational banking data. Guess what types of analysis you could run on their transaction patterns? What if you also measured total value instead of count? Handling data quality issues in banking views. Missing or duplicated IDs cause broken joins. Negative or zero amounts can signal data capture errors. Always check for unexpected nulls or out-of-bounds values after merging. Print samples early and often to catch mistakes before deeper analysis. Running the cell now. A classic error, negative or zero transaction amounts, which banks must review and fix. We filter for transactions with suspicious amounts at or below zero and print a sample to investigate. Running the cell now. This output shows a sample of transactions where the amount is zero or negative, highlighting potential data quality issues such as incorrect or reversed entries. Notably, negative amounts appear across both credit and debit transaction types and various channels, signaling a need to investigate these anomalies before proceeding. Printing such samples early helps catch and address unexpected values that could distort analysis or break downstream joins. What might cause negative amounts in real systems? How could false positives be minimized in production? After merging, always check for null IDs. Nulls signal join errors or missing master data. We filter the merge table for rows where the customer ID is null, which should not happen if all data quality checks passed. Running the cell now. This output shows that there are no missing customer_ID values in the merge dataset, which is crucial because missing IDs would indicate broken joins and incomplete data. Noticing this early confirms our merge was successful and sets a solid foundation for further analysis without losing transaction records. If nulls exist, what is your next step? Always trace back to the join keys and investigate missing source records. Best practices in building bank data views. Always start by profiling data for nulls and range errors. Use explicit joins and always check output shapes. Verify all ID relationships before business analysis. Use meaningful column names so business partners understand your work. Save clean, intermediate tables as checkpoints. Running the cell now. Let us save our clean, merged transaction data for future reporting and compliance needs. We save the merge data frame to a CSV file for downstream analytics and business use. We print a confirmation message to show the file has been written successfully. Running the cell now. This output confirms that the cleaned and merged customer transaction dataset has been successfully saved as a CSV file. Saving this intermediate table acts as a checkpoint, ensuring the data transformations and joins are preserved before moving on to further analysis. This practice supports traceability and collaboration with business partners by keeping data organized and accessible. Now opening the cleaned customer transactions file so you can review the saved core banking view. Try opening the CSV to verify column structure. What file formats might be better for larger datasets? Let us now solve a real-world case. What is the total monthly debit flow per customer segment for the bank? We comment code for an end-to-end banking view calculation. We extract month from each transaction for monthly tracking. We enrich transactions with customer segment using a join. We filter down to debit transactions and sum the amount by both month and segment. We print out the resulting view, monthly debit value per segment. This is a real bank analytics table. Running the cell now. This output shows the total debit amounts by customer segment for each month, with a clear pivot table format where rows represent months and columns represent segments. Notice the shape confirms the join preserved data as expected, and the meaningful column names like business and retailer make it easy for business partners to interpret the results. This step verifies ID relationships and aggregation logic before proceeding with further analysis. Think, how could this view support early fraud warning or product performance meetings? Try changing to credit transactions. Watch part 2 of this tutorial on YouTube for more advanced customer lifecycle analytics. Final practice: what percentage of business customers by region make at least one credit transaction? We begin with a comment describing this advanced business metric. We filter merge transactions to business segment and credit transactions only. We calculate the count of unique business customers with at least one credit transaction by region. We get the total number of business customers per region from the customers table. We divide the active count by the total, convert to percent, and round to 2 decimal places. We print the final percentage share of business customers active per region. Running the cell now. This output shows the percentage of business customers in each region who made at least one credit transaction, calculated as 90% for the regional region. Notice the importance of filtering by segment and transaction type before grouping and the key use of unique customer counts to avoid duplicates. This aligns with best practices by verifying ID relationships and producing a clear, meaningful metric for business analysis. Challenge: could you use a similar logic to track dormant customer bases? If you enjoyed this lesson, search YouTube for more open banking Python analytics.